In this part, we're going to talk about the ways we get energy directly from the sun. And the most common way that you may be familiar with is through something called solar photovoltaic uh, energy. And this is a technology that directly converts the energy of photons into electricity. We're not going to worry about the nuts and bolts of how photovoltaic technology works, which is what's really illustrated on this slide and the next two slides. The point that I want you to take away from this is not worrying about N-type semiconductors and P-type semiconductors so much, is more that this type of technology acts on the atomic level with individual photons causing electronic charges to move and rearrange themselves within this photovoltaic cell that's composed of different materials that allow themselves to absorb that solar energy and separate the charge. And when that charge is separated, it's sort of like you've created a battery. There's a negative terminal and a positive terminal, and then I can connect the negative terminal to a wire and the positive terminal to a wire, and then I can hook those up to a light bulb as shown here, and the current flows through from the negative through the light bulb to the positive because opposite charges attract. So the sunlight is driving those charges apart within the semiconductor, within the photovoltaic cell, and then by hooking that up to an electric circuit, I can get a flow of electricity. And this is fundamentally different than the types of electricity generation that we've talked about up until now, which have involved converting some sort of energy to thermal energy of steam, and then using that steam to create kinetic energy of a turbine, which then uses electromagnetic effects to generate a flow of electricity through a circuit. This doesn't have anything to do with thermodynamics. There is no thermal energy involved in a photovoltaic cell. It's completely uh, independent of the efficiency limitations of thermodynamics and the processes of thermodynamics at all. So it's a very different kind of electricity generation than what we've seen in fossil fuel power plants and nuclear power plants, and in fact, different than what we will see when we talk about wind in the next module. So this is what one of these photovoltaic cells looks like up close, and the challenge of these are there's not a thermal component, you don't have a fuel to burn or waste from the fuel or anything like that. It's sunlight directly into electricity. Then it just becomes a technological challenge of how efficiently and how inexpensively can we make these photovoltaic cells. And at the time that this particular slide was made from, I believe, the second edition of your textbook, uh, the cell had a 14% conversion efficiency, and this particular little cell shown here produces electricity at a rate of 2 watts, 2 joules per second of electrical power coming from that. At 14%, you're like, oh, that's terrible. Well, as you'll see when you work through the assignment, there is a tremendous amount of sunlight available. That just means that we need more panels in order to get as much electricity as we could if that efficiency were a little bit higher. Since this time, efficiencies have increased. And for example, I've got solar panels on my roof, solar photovoltaic panels on the roof of my house, and they're 20% efficient. And they were just sort of standard photovoltaic panels that you buy for your house. Now, there's a limit to how high that number can go. We will never have 100% efficient solar photovoltaic panels, but we don't need to. So you get a lot of those cells together, and we uh, hope that they can be economically competitive and viable, so it's not too expensive. And they come in panels that are 1 to 2 square meters in size, and then you put a whole bunch of those panels together and create an array. So here's what another panel looks like. This one uh, produces 240 watts of power is what its rating is for noon. Uh, there's a particular standard for like what angle the sun is coming at to determine a solar power's rating. solar panels rating. So 240 watts is very much on the low end now. So this figure is just a few years old, but current panels are all over 300 watts of power. The ones on my house are 325, and my neighbor just got some that are 360 or 370. So the technology has been improving rapidly, and at the same time, costs have been coming down as well. And you'll see these panels on the roofs of houses. Uh, not tremendously common, but maybe 1% of the houses in the Orlando area seem to have them. You'll also occasionally see them on smaller installations, so sometimes you'll see them powering an emergency warning sign or something like that along the side of the road, where that's something where crews need to set something up that needs electrical power, but there's no outlet available. Well, if it doesn't need a huge amount of power, you just have your own little solar panel on it, and that charges up during the daytime, and maybe you have a battery to help it go overnight. Now, if we talk about utility scale generation of electricity from solar, then you just need a lot of area. The sunlight is coming in a certain number of watts per square meter. That's joules per second per square meter. So the more square meters you've got, the more watts you've got coming in that can be converted to electricity. So here's a picture from your book showing a 550 megawatt solar power installation in California. That's half a gigawatt. That's about half the size of a typical fossil fuel burning power plant in terms of power generating capacity. That's its rating. Of course, a fossil fuel power plant can be producing that level of electricity overnight, and the solar plant cannot. Um, Here is another sort of scale comparison. Uh, on the back, you see a nuclear power plant, 1,000 megawatts, that's a gigawatt. And the nuclear reaction is taking place in the smaller concrete dome that you see there in front of, closer to us than the two cooling towers. That's where the nuclear reaction is taking place. And they've installed a small solar photovoltaic plant sort of in their backyard. And the power output of that solar photovoltaic plant is 2 megawatts, or 500 times smaller than the output from that nuclear power plant. So solar power requires a certain amount of surface area in order to produce a lot of electricity. Fortunately, we have a lot of surface area. And as you'll see in the assignment, the surface area available is more than sufficient to supply human electricity needs. This shows the distribution of utility scale solar photovoltaic solar power plants in the United States as of a few years ago, and this is something that's been evolving quite rapidly. And you can see there's a concentration in the Southwest, and we saw previously that that's where we have abundant solar energy due to being at a low latitude and having predominantly clear skies. But you'll also see that there are some very strong clusters that don't seem to really line up with what the solar resource is. And that just has to do with political incentives for producing solar power. So if local governments, state governments incentivize utilities to produce power from the sun, then you will get a bunch of utility scale solar power plants. As you see in North Carolina, there's a big cluster. And in the New Jersey, Philadelphia, and New York area, there's a much larger concentration of those. And that has to do with political decisions to say we want to have more of those, and not with what's the weather actually look like in those power plant stations. Closer to home, of course, here's a small system at Disney World. A new system has recently come online that's 10 times bigger than this, and there are a number of other systems that have been built in Florida by the local utility companies as well. And the growth of solar photovoltaic capacity is exponential, and this is one of those times when exponential growth is a good thing. Bad things can grow exponentially, like debt, but good things can also grow exponentially, like the balance of your savings account. So this figure from your book, uh, which was shows data to 2016, is the total rated capacity and power output of solar photovoltaic uh, facilities connected to power grids in the world. So connected to the power grids means not just owned by utilities, but also the one on my house is connected to the power grid. And what that means is that right now, I'm recording this in the daytime. It's sunny. That so the solar photovoltaic panels on the roof of my house are currently producing more electricity than my house is using, and the excess electricity is connected to the grid and is being used by Duke Energy, my utility, to supply power to other houses in the grid. So Duke Energy is burning less natural gas to supply those houses electricity. So it's essentially a miniature electricity utility on the roof of a house. The vast majority of solar photovoltaic plants in the world are grid connected like that. And you can see that the growth has been something like 40% per year, which is just huge. That's a doubling time of less than 3 years. And in fact, I looked up the numbers since this was published, and the global installed capacity of solar photovoltaic at the end of 2019 was 583 gigawatts, and you can see that in 2016 it was about 270 gigawatts. So from, sorry, 2016 it was about 270 gigawatts. So you can see that from the end of 2016 to 2019, in 3 years, it did more than double. And so that very, very fast rate of growth is continuing. And if it continues, that would mean that by the year 2022, the global installed capacity of solar photovoltaic would be more than 1,000 gigawatts or more than a terawatt of electrical power available.